Okay, so this is the review packet for the honors students. If you are not in the honors class, go check out the other video for the other sheet. Okay, which compound dissolves in water to form an aqueous solution that can conduct an electric current? So we're looking for electrolytes, those are acids, bases, and salts. So we want an acid, a base, or a salt. So how about reference table K, table L? Find an acid, find a base. And here is acetic acid. So that is our answer. This should be an L, not a 1. CCl4, that's an organic compound, that's carbon tetrachloride. The second choice is an alcohol, and the fourth choice is methane. So those are not acids, bases, or salts. Now, what is a salt? That's an ionic compound, and they have to be aqueous, so it says dissolve in water. As water is added to a 0.10 molar NaCl aqueous solution, conductivity will, okay, so you are adding water. So if you add water, that means you are diluting something. So if you are diluted, your conductivity will not be as good. Think about this. If you were given poison, concentrated poison, you would get sick or die almost immediately. But if you were given very dilute or watered down low molarity poison, it would take a while. So yeah, you want it to be one of those. Then you say, okay, the conductivity, the resulting ions, because the concentration of ions would decrease. That's right. The concentration would be a lot smaller because there's all these water molecules now. Substance is classified as an electrolyte because it conducts electric current, electrolyte. Number 4, a student has a 0.1 molar aqueous solution, conducts electricity. Blue litmus goes to red and reacts with zinc to produce a gas bubble. We've actually done that in the lab. So conducts electricity means acids, bases, or salts. So I'm going to get rid of anybody that's not an acid, base, or a salt. This is an alcohol. If you don't remember why, that's because this is organic, containing carbon with the hydroxide. This could be a salt because it said it was aqueous. This is an acid, and this is a base. So that's that one. Blue litmus turns red. So we need to go to reference table M. So when litmus turns red, that's a low pH value. That's 4.5 or lower. So low pH values are going to be acids. So there's our answer. And also, if you had zinc plus HBr, this is a single replacement. Zinc is higher than hydrogen, so you get H2 plus ZnBr2. This is not balanced, so you do it like this. But you see how we have the bubbles? That's hydrogen gas bubbles. So that's why you'd have the bubble. So choice 3 is our acid. That's our answer. Which is a non-electrolyte. So we're not looking for acids. We're not looking for bases. We're not looking for salts. This is on table K. It's an acid. Table K, acid. That's on table L, base. Yeah, here it is. This is organic. This is an alcohol. Choice 4. Number 6, which is the best conductor of electricity? So we need acids, bases, or salts, and we also need them in solution, aqueous. So no solids. So now which of those is an acid, base, or a salt? This is table salt, ionic. That's why that's our answer. This is sugar. That's a molecular compound. Arrhenius explains the behavior of acids and bases. Yeah, that's the only one that makes sense. Arrhenius acids produce H plus in solution. So which of these is going to give off H plus in solution? Here's another thing you could do. Just look at table K. If it's on table K, it works. So there's our answer, choice 3. Arrhenius bases give off OH minus or hydroxide in solution. So only 3 and 4 have OH minus. But it's that tricky one. Bases versus alcohols. Alcohols are organic. Bases are inorganic. So if you see carbon, this is not a base. This is an alcohol. Potassium is inorganic. That means it's not carbon. So that's our answer, base. What is the only negative ion produced by an Arrhenius base in water? That's hydroxide. Definition. According to the Arrhenius theory of acids, citric acid in oranges and acetic acid in vinegar are classified as acids because they, Arrhenius acids give off H+. What is H+? H+ is hydrogen. Is it an ion or an atom? Well, the fact that it's got a plus means it's got a charge. It's an ion. What is the pH of a solution that has a hydronium ion concentration 100 times greater than a solution with a pH of 4? Okay, so let's go back. There's a couple things going on here. Hydronium is water and an H+ or a proton. So this means acid. So this means you want a stronger acid. Now, pH scale. Each jump on the pH scale is worth 10, logarithmic. I don't have all of them. So pH of 4, we start at 0, 1, 2, 3, 4. We are going 100 times greater acid. It's going to be 1, that's 10, 2 is 100. So it's a pH of 2. 100 times less acidic would be a pH of 6. And then 3 and 5 don't make sense. As the pH of a solution changes from 3 to 6, what happens to the hydronium ion? So remember, hydronium is H2O, water, plus an H+. So that's acid. So if you're going from 3 to 6, so here's 3, this is going to be less acidic. So you're going to have less acid, decrease. But what are you decreasing by? A factor of 3 or a factor of 1,000? So look, this is 1, 2, 3 jumps. Don't be confused and say, oh, it's 3. Remember, each jump is worth 10. So that's 10, 100, 1,000. Choice 4. H+, I've been saying this forever now. H+ in solution is going to be, let's see, here's H+ and aqueous solution. So that's 3 H's and an O with the leftover plus. That's called hydronium. Let's scooch it down. Which statement correctly describes a solution with a pH of 9? pH of 9, high pH, it's a base, which means you are a base. You have more hydroxide. So it's not 3 and it's not 1. Now, bases, will they cause litmus to turn blue or will they cause methyl orange to turn red? I need to look on table M because I don't know off the top of my head. Litmus will be blue, pH of 8.3 and higher, and so that fits for 9. Methyl orange is there's no choice to be. Methyl orange should be red, 3.1 or lower. So no, that's not the answer. So it's got to be choice 2. Number 16, given these, which list has the solutions placed in order of increasing H+? Increasing H+ means you're becoming more acid. So if you're going from 10 to 7 to 5, this is base, this is neutral, this is acid. So you want A, B, C. Choice 1. All right, remember the brackets around mean concentration. Which relationship is present in a solution that has a pH of 7? 7 is neutral. Which of these represents neutrality? That means when you have the same amount of hydrogen ions, acid, as you do hydroxide ions, base. Okay, given the ionization constant equation, W means water. So water, you know, is neutral pH of 7. So you have those multiplied, give you that. So if water is neutral, that means once again we have equal concentrations of hydroxide and hydrogen ions. Okay, if the OH minus concentration is 1 to the minus 4, what is the H+? So remember, these two things multiplied must give us 10 to the minus 14. So if hydroxide is 10 to the negative 4, how am I going to get to 10 to the minus 14? I need 10 to the minus 10. I am assuming a certain level of math for this that you are familiar with, exponents and that kind of stuff. If not, just remember the exponents always have to equal minus 14 for Kw, which is neutral. Okay, what is the pH of that? Now, I did give you the pH formula. pH equals negative log of the H plus concentration. Or you could just say, I need to move my decimal place until I get to the whole number 1. So I have 0, 0, 1. 1, 2, 3. There it is. That is not a super big concept, so if that's confusing to you, don't stress about it too much. The H3O plus concentration, that's hydronium, is 1 times 10 to the minus 4. What is the solution? Now, there was a worksheet that we went over with pH and pOH and concentrations. So if the H plus concentration is 1 times 10 to the minus 4, that means the pH is just a positive exponent of 4. So there goes that, and there goes that. pH of 4 is an acid. That's just straight up definition. Here's another one. That is 4 zeros. 1, 2, 3, 4 zeros, and a 1. So move the decimal place until you get to a whole number 1. So that's 1, 2, 3, 4, 5. There's our answer. pH of 5. Which indicator is blue in a solution that has a pH of 5.6? I need reference table M. So brome cresol green is blue higher than 5.4. So that could be our answer. Let's just double check the rest. 7.6 or higher for brome thymol blue, so that's not going to do it. Methyl orange does not give us the option to be blue. Thymol blue is only blue in a super high pH of 9.6, so it's got to be choice 1. Which indicator is yellow in a solution with pH of 9.8? So 9.8 methyl orange. That could be our answer because 9.8 is to the right of 4.4. You need to be looking at table M. Brome thymol blue is yellow in low pHs. Brome cresol green is yellow in low pHs. Thymol blue is yellow 8.0 and below. And so since we have 9.8, it has to be choice 1. According to reference table M, what is the color of indicator methyl orange in pH of 2? Methyl orange, pH of 2. So you notice that 2 is below the range on the left. So that's the color on the left, which is red. And also get rid of colors that don't make sense. There's no blue in methyl orange. And there's also no orange in methyl orange. Now, why would that be? Well, remember that unknown range in the middle? That's where the orange would be. A solution with a pH of 11, whoop, whoop, that's base, is first tested with phenolphthalein and then litmus. What is the color of each? Now think of the titration lab. Phenolphthalein in a base is pink. Now phenolphthalein with a pH of 11, litmus with a pH of 11, that's going to be blue. It's very high, so that's going to be choice 3. Which particle in a water solution of sodium hydroxide causes red litmus to turn blue? So litmus is turning blue in high pHs. High pHs are bases. Bases use hydroxides. Okay, so now we have some Bronsted-Lowry. The Regents calls these the alternative theory or the alternate theory. Bronsted-Lowry acids and bases. Acids donate. Bases accept. I think Mrs. Davis has another way of saying this. Bad. Bases accept, acids donate. This is the bad theory. I don't know. Whatever. This is all about donation. So the H plus acceptor for the forward. You don't even need to know if it's acid or base. Who is gaining H plus going this way? NH3 becomes NH4 plus. Right there. There it is. So it's choice 2. First of all, your only 2 choices would be those first 2 because these would be gaining going that way. So NH3 becomes NH4 plus. That's obviously gained H plus. H2O becomes OH minus, is losing. According to the alternative theory, Bronsted-Lowry, H2O is considered to be a base when it accepts protons. All right, the 2 acids. Now, this is not, I don't love this question because it assumes that you know they're talking about Bronsted-Lowry. So the two acids are the Bronsted-Lowry acids, which means they donate protons. So HNO3 becomes NO3. So that means that's an acid, which means this is a base. H3O plus becomes H2O. That means it's losing, so that's our acid. This is a base. So we got HNO3 and H3O plus. So that's choice 4. Yeah. Okay, what does water do? Well, look, it doesn't matter which one you choose because water is getting or is accepting, and water is also donating. So it's both a donor and an acceptor, and that's called amphoterism. Amphoteric. That means you exist on both sides of honors reference table L. And I wonder if it's coming up. What is the ionization constant Ka of acetic acid? So that is honors reference table N? No, L. L. So honors reference table L. Acetic acid is HC2H3O2 or CH3COOH. So you're looking for either one of these formulas. And by the way, if you didn't know what the formula for acetic acid is, look it up on regular old table K. So now I'm back on honors table L. What is the Ka of acetic acid? I find it's about halfway down. 1.8 times 10 to the minus 5. There it is. I just looked it up. This talks about how strong of an acid you are. The higher the Ka, the stronger the acid. So you see that Ka of acetic acid is mid-range. So it's not a super strong acid, but it's not a very weak one either. And as you've ever gotten vinegar in a paper cut, you know it's kind of strong. Based on honors reference table L, which is the strongest electrolyte, which means the highest Ka, because it will give off the most particles here. So H3PO4, that is in the upper third. HNO2 is below that. HCl is third from the top. And HF is almost halfway down. So the highest is HCl, which means that's the strongest electrolyte. It breaks apart into the most particles. Which of the following Ka values for 0.1 molar acid would have the smallest of that? So if it's the smallest hydronium, that means it's the weakest acid. So you want the lowest number, okay? So who's the smallest number? Well, let's take a look. Let's look at exponents. Who's this? Okay, -10. That's going to do it. That looks to be, does it represent anybody on here? 5.7. It's not anybody necessarily on table L. All right. Here we go. Based on honors reference table L, excuse me, which compound is the best conductor? Again, highest on the table. HF, midway, H2S, lower, H2O. Almost to the bottom. H2SO4, it's a large Ka. That's our answer. Who has that value on honors table L? So I'm going to find it. Okay, so it's a little below halfway. CO2, that's carbonic acid. How did I know that? By the way, you say, oh, there's carbon dioxide. Well, when it's an aqueous solution, it's called carbonic acid. So that's a combination of honors reference table L and regular reference table K to figure these out. What happens in H2O of these two reactions? Okay, so in the first one, H2O becomes OH minus. What happened? Gave away. So that isn't Bronsted-Lowry acid. In the second one, it gains. See how we went from H2O to H3O plus? It's gaining. So water acts as an acid in X and a base in Y. So that's choice 3. Excuse me. Which is amphoteric or amphiprotic? That means you can act as either a Bronsted-Lowry acid or base, meaning if you're looking at honors table L, it's on either side. Okay, so you'll find it under the column for acids and under the column for bases. So HI, I see HI at the top on the acid side. I don't see HI on the right side, so that can't be it. NH3, well, I know NH3 is a base, so I do see it on the right side. It's like a third of the way down. But I also see it on the left side, acid, all the way at the bottom. So that means that's our answer. Go ahead and check. These shouldn't be on both sides. What is the conjugate acid of the hydroxide ion? So remember it says acid and then equals and then base, H plus base on honors table L. So find OH minus here for base. It's the third from the bottom, which means your acid would be H2O. This stuff is no longer on the regents, so I wouldn't stress too much about it if you're not going on to higher level chemistry or bio. Which of these is basic? That means you want to talk about hydroxide. Hydronium is acid. So if you want to be basic, you have to have it greater than the middle, greater than 7. That's our answer. Oh, another one of these. So if you are 0.01, that's 1, 2, pH of 2. Move your decimal place until you get a whole number. All right, NH3 goes to NH4 plus. So that means it's gaining a proton, which means it's a Bronsted-Lowry base. And it's not an acid, so it's just 2. Scroll on up, home stretch. Amphoterism again, so you need to exist on both sides of reference table L in the honors place. H2S, I don't, okay, it's on the acid side. I don't see it on the base side. You need to be looking at honors reference table L. If you don't, you're not going to be able to see this. HS minus is 4th from the bottom on the acid side. HS minus. Oh, it's also about 2/3 of the way down on the base side. That's our answer. Conjugate acid-base pair, so this is Bronsted-Lowry. That says BL. NH3 goes to NH4, which means it's accepted, so that means it's a base acid. NH4 goes to NH3, that means it loses, so there's the acid base. So now, conjugate acid-base pairs just say, okay, we got base on one side, acid on the other, acid, okay. Also, if you don't look slightly similar, like these don't look anything alike, neither do these, and neither do these. So I actually didn't need to do any of that work. I just say, well, what's the difference between, and I hate how this is on 2 lines, I'm sorry. What's the difference between those two? Well, it's a proton, which means, hey, that's our answer. Neutralization, that's acid plus base equals salt plus water, yields salt plus water, excuse me. So I don't see an acid here, or here, or here. Boom, answer. Choice 3. Which reactants form the salt? CaSO4. So that means that's a product. CaSO4 is a product. And we'd have HOH or H2O. So that means if this is a double replacement, let's work in reverse. So Ca is not going to be with this. Ca is going to be with OH. And of course, I'm kind of going fast. You have to crisscross your charges. HSO4 would be what we have to start. H and SO4. And of course, you'd crisscross and you get that. I did a reverse double replacement because that's what a neutralization is. It's a specific kind of double replacement. So which reactant will form that? So we want H2SO4 and that. Yeah, choice 3. I did that fast. I know. So if that was too fast, you need to reach out and ask. Which is a salt? A salt is an ionic compound. So nobody on table K, nobody on table L. This is on table K. It's an acid. That's not our answer. This is on table L, not our answer. This is on table K, not our answer. So there it is. Na is positive 1, nitrate negative 1. Okay, now we got some titration. So let's get our calculators out. So we have NaOH. My OH minus equivalence is a 1, and our H plus equivalence is a 1 here. How did I do that? I think I've done it a few times, but anyways, break it apart. So that's going to have our Na plus OH minus. How many hydroxides? Just 1. So notice how they're both 1s, so it's not going to change anything. So if we're looking for NaOH, its base, so our volume of the base is what we're looking for, 0.10, that's a 0, sorry, and this is volume of the base, and 15 milliliters of 0.20, so 0.20, 15, okay? And again, we would put a 1 here and a 1 here if you really want to be on top of things. So let's get our calculators out. 0.2 times 15 equals 3, divided by 0.1 is 30. So there's our answer, choice 4. Scooch this down a little bit. A 16 milliliter sample of 0.50 KOH, its base, will completely neutralize 32 milliliters of what? So we're looking for molarity of the acid. So there we go. 32 is our volume of acid. 16 is our volume of base, and 0.50. Notice how I didn't go in the same order because it's commutative property of multiplication. So 0.5 times 16 is 8, divided by 32 is 0.25. There it is. A 9 milliliter sample of HCl solution is exactly neutralized, blah, blah, blah. What is the concentration of HCl? So HCl is an acid. Molarity of the acid is what we're looking for. We have 9 milliliters. Sorry, that's a 9, messy. 6 milliliters of base, 3. And forget the decimal place. So 6 times 3 is 18, divided by 9. Why did I put that in my calculator? It's 9. I screwed it up. 6 times 3 is that. See, pride cometh before the fall, they say. 18 divided by 9 is 2. And there's our answer. Okay? So I went through that kind of fast. Please, if you got anything wrong, take a look through your notes. Try to figure it out. If you still have questions, absolutely contact me, and we'll get it worked out. All right. Thanks, guys. Good luck. Take care.